Welcome back to the PLC Professor's video library. The PLC Professor presents another how-to, and this time the subject is building an advanced controller interface. We have a video already to build a basic controller interface, and that is attaching a Micrologix 1010-point controller to a project box with 6 toggle switches and a 24-volt DC power supply. So this one's very similar. Actually, I sat down to build this box for my own purposes to use for the new manual that I am about ready to print for RS Logix 5000. It'll be a couple hundred pages in color with lab projects for mostly compact logics, but some included for control logics. And as I sat down to build, I thought, why not just turn on the camera and record the bulk of the process? And as I was doing that, I realized a little information up front would be good. So I made a part 3 to the physics playlist, part 3 to the principles of electricity magnetism. Actually, it's a part 3A and B, where I talk about controlling the electrical state of the copper traces on a backplane. And basically, it is in support of what we're going to do right now. Now, there are 2 series in this subject. The one I just mentioned, which is the lectures leading up to building the device. And this is going to be the second section. Actually, I guess there's 3. So there's the basic principles of the electrical state of the backplane. So that would be principles of electricity and magnetism, part 3A and B. Then there's the one we're doing right now, which is going to talk about what we're going to build and why we're going to build it. And then there'll be a third section that is all videos of actually putting the box together. Now, not all the videos came out real great, and since I only built one of those boxes, I can't go back and redo them. There were a couple where I bumped a button on the camera, got lower resolution, and one other time I bumped a button and it took out all of the red. But it's still pretty good. If you're a panel builder, you can visually substitute the backplane terminal strips and etc. while we are doing the build with components from electronics supplier using very inexpensive switches, LEDs, and potentiometers. If you have not watched the video on the electrical characteristics of backplanes, then I would stop this video and go watch it first, because you'll see that this starts out with a review of that video and then continues on. That is, of course, unless you are already extremely familiar with backplanes. If you have watched that video, Principles of Backplanes, this is a bit of a review in the beginning of the components on the backplane. First, we add connections to the backplane from a circuit board. To control the activity on the backplane, we add electronic switching to control the interface to the backplane from this module. And of course, we need a CPU to follow our instructions. Random access memory to store the list of instructions and the results, as well as the image for input modules and output modules. Firmware to support the capabilities of the instructions. Communications electronics and communication ports. And this is our processor module. We need something to process, so we add an input interface to the outside world. So we add some more connections to our backplane, connections to the outside world, electronic switching to control whether or not the outside world is actually connected into our backplane, and this is the input module. Now, we went over this in more detail in part 3 of the basics of electricity, magnetism, electrical characteristics of backplanes. You will also find a couple videos in the lecture series in the playlist lectures As you get further in, there's about 12, 13, 14 lectures, about 7 hours, I think. As you get in a couple of them, I go through this exact same material with completely different graphics. So the more different angles and views you can have of this, the better you'll understand it. So here we have a processor and an input module. Now, we want to get something out of the backplane. So we add some connections to the backplane, and then we add connections to the outside world. Electronic switching to control the interface between the outside world and the backplane. This is our output module that receives electrical states from the processor, transferring out to the actual field devices such as solenoid valves, motor starters, indicators, and other electrical interfaces. Now let's simplify our diagram to go to the next step of this presentation. So we're going to leave this graphic format and go to something slightly different, simplified. Okay, so here we have an input module, we have a processor, we have an output module. But we've simplified it so we can add some more information to our graphics. This is where we start adding the components that we will use in our advanced trainer construction in the next portion of this series. So let's add a toggle switch and a push button. These are the actual toggle switches and push buttons that I use. We need a source of EMF or voltage, so we connect the positive side of our power supply, our direct current power supply, to one terminal on each switch. So now, if you look at the top switch, that toggle switch, typically you see the toggles flipped up. That will connect the center terminal to one of the other two. Now it really doesn't matter which one you use, because you can flip the toggle switch, one direction is off, the other direction is on, as far as the center terminal to one of the others. So in this case, we're only going to use one side of that toggle switch. So we attach the positive side of our direct current power supply to one terminal of each switch, and we connect the other side of the switch to the first input terminal. So in this case, that toggle switch right now would be off. When you flip the switch down, then it'll connect the top terminal and the middle terminal. So basically, these two switches, the toggle and the push button, are wired in parallel. Either one of them will put 24 volts DC on that screw terminal on that input module. And the reason we do this is, in the past I've always used toggle switches, and there were times when I found it annoying when I wanted to just pulse something. I had to flip the switch and then flip it back. And if I flipped it and forgot to flip it back, it stays on and it messed up my little experiment. So what I do now is I add a push button in parallel with a toggle switch, and if I want to use it as a momentary, then I just leave the toggle switch off and I use the push button. Either one of them will turn the input on. And then we need a common, so we add another screw terminal to our input module. So now we have 0 volts DC and 24 volts DC. Now 0 volts DC is negative compared to plus 24. But typically with DC power supplies, you have 0 and you have something else. But comparing it to the battery we used in earlier presentations, the black is the negative side of the power supply. These illustrations show how to connect field devices to a 1769 IQ16F DC input module. Now this is exactly what I'm using on my little hardware demo with Compact Logics. However, 1769 is the family of compact I/O modules that works with micrologics, a model of micrologics as well as compact logics. So if you have even another brand of PLC and I/O modules, you can adapt this advanced training demo to whatever hardware you have. You just have to keep in mind this is the wiring diagram that we're using, and it's from the IQ16F module. Notice that positive connects to all of the switches. So you see the positive. Now, by the way, this is a universal I/O module, so you can wire it up in either polarity. You can't mix the polarities per group, but you can wire up 8 of the inputs as positive common and the other 8 as negative common if you want. So you could actually take this 16-point input card and use 0 through 7 as supplying positive to the sensors, or you could use the inputs 9 through 15 to supply negative to the sensors. Now when it comes to syncing and sourcing, I have a whole lecture on that, and it's towards the end of the lecture series in the playlist. You find lectures, you go to just about the last one. I think it's called Miscellaneous. There's a little talk in there on syncing and sourcing, so we won't go over that with this one. And then of course the negative side of the power supply is hooked to the DC common, not to the devices, to the DC common. So when any of these switches closes, electrons come in common 1 DC, go up through the circuitry of the card, through the switch that's closed and up to the positive side of the power supply. And as I said, this particular module can be connected with either polarity, and we just picked one. Now this is an example of one input connection, and when we go to building our little box, we'll use 10 of these toggle push button combinations on our actual construction project. We are going to use LEDs for outputs. So LEDs require a dropping resistor, and I purchased mine as 24 volt DC LED assemblies, which means they came with the correct resistor already connected in series with the LED. LEDs are diodes and polarity sensitive. If when you get done with your project they don't light up, you probably connected them in backwards. They are polarity sensitive. Now I didn't pay any attention to my graphic here for an LED, whether I had positive or negative. It doesn't matter to me. I'm just saying that you have to pay particular attention. Now these assemblies that I buy, it's an LED with a resistor, it's shrinked, tubed, and it has a red and a black conductor coming off in pigtails, red positive, black negative. That way I don't have to worry about polarity. It's indicated by the color of the wires. And in the third grouping on this particular subject, you'll see the assemblies that I'm working with. We need the positive side of the power supply going to the output module, because remember we want to feed 24 volts DC to our output devices. And the negative side of the power supply again goes to the common. The LED connects to the first output terminal, and the other side of the LED attached to the negative side of the power supply. So we connect up the LED to the output terminal, and then we connect up the other side of the LED to the negative side of the power supply. This is the wiring diagram for a 1769 OB16P output module. Again, it's part of the compact I/O, and it is specifically what I'm using in my little hardware trainer that I use for developing the RS Logix 5000 manual. The positive side of the connection and the negative side of the connection. Now notice that this is polarity sensitive. You can't reverse the positive negative and expect this to work because it's a solid state output control. Well, alrighty then, we have one of each connected into our demo now. We have an input and an output. Processor in slot 0, output card in slot 1, input card in slot 2. Now the next discussion involves a lot of detail, most of which we will not illustrate with graphics at the level that we have done so in other presentations in the PLC Professor video series, whether on YouTube channel or on the disk. But the basics are still covered. Remember, we are leading up to building a hardware interface to a controller for doing lab projects. And the one that we're building can work with any PLC. You just have to watch your polarities. We are going to maximize the RAM here for the sake of illustration. We call out our processor slot 0, output slot 1, input slot 2. Now see, they're not in order there, but I just happen to assemble them with the processor, then the output card, then the input card. But because we read from left to right, I have the inputs coming in, the processor does some thinking, and the output's going out to the right. That's why we did our graphic this way, but we'll switch it around later. So we have identified the first input terminal as that which controls the state of memory location I:2.0/1, which would be read I for input, 2 for slot 2, 0.0 for the first word of that slot, since some modules support more than one word of data per slot, and then /1 for the bit that we actually have it connected up to. Actually, it's slot 0. It's /0. So it's input delimiter colon slot 2 delimiter word 0 delimiter bit 0. That is the memory location that those two switches together are going to control the state of. We have also identified the output terminal as that which is controlled by not controls, but controlled by the state of memory location O:1.0/1, which would be read 0 for output, 1 for slot 1, 0.0 for the first word of that slot, since some modules support more than one word of data per slot. Now these only support one, but the addressing scheme still stays the same. And then slot 1 for the actual bit in that word that is going to control that output that controls that device. This means that the state of that bit in memory indirectly determines whether the LED is on or off, reflecting the state of the memory location. So if the PLC is running and that bit is on, then the LED is on. If that bit is off, then the LED is off. That is, if the PLC is in the run mode. Next, we download one single rung of logic, of relay ladder logic diagrams, whatever you want to call them, into memory. Place the controller in the run mode. The state of the input is off, the rung is false, the output bit is off, and the LED is off. So here we have one input connected, one output connected, and in our random access memory we have actually two instructions, and these two instructions logically are in series. One of them is a condition and the other is an action. The first instruction is a true if on. If that memory location I:2.0/0 is on, then that instruction is true. That is a condition. It's true or false. On the other end of the rung, we have an OTE, output energize instruction. It's never true or false. It's either on or off. But if the rung is true, that instruction addresses O:1.0/1 and tells it to be on. If the rung is false, it tells it to be off. So that second instruction that addresses O:1.0/1 has a true execution and a false execution. But when you look at that instruction in your online monitoring, it is either on or off, never true or false. But the first instruction is never on or off, it's true or false. Now, if that bit I:2.0/0 is on, then that instruction will be true. So you might say, well, if it's on, then that's on. Well, you'll see later, you don't want to think on or off when it comes to conditions. You want to think true or false, always. When it comes to actions, it's on or off. So, let's energize an input, either by flipping the toggle switch or pushing the push button. That puts 24 volts DC on that terminal, and if that module is activated, meaning the processor, when it does an I/O scan, it reads in I/O inputs first, it does the program, the instructions, then it scans the output cards to update them. So the next I/O scan, the processor energizes the electronic switching in the input module, and the on state of the switch is felt on the backplane. The processor reads in the state of all of the inputs, and since the first input is on, it turns on that bit in memory. The next time the processor scans the logic, it reads that memory location is on, and therefore the instruction is true, because that's a true if on instruction. The rung, therefore, is true because that's the only condition in it. And it sets the bit in memory that the second instruction is addressing, or the output bit that will control the LED. So you turned on an input, the processor read it into memory, and then when it scanned this rung of logic, it read that memory location, I:2.0/0. It read it because this instruction, this true if on, addresses that memory location. Therefore, it's true. That makes the rung true because that's the only condition. And then the second instruction tells O:1.0/1 to be on. The next I/O scan, the processor puts the word for the output card onto the backplane, and on comes the LED. Now there's a little bit more electronics involved than what we're showing here, because remember, the cycle for this processor, simply put, is it does an I/O scan, it reads in the inputs, it takes a snapshot of the state of those 16 inputs. I show more than that screw terminals because remember, we got a 32-bit backplane, but it's only a 16-point card. So it reads in those input conditions and puts them in a word memory. Then the logic scans, and there's only one rung of logic. It goes and reads bit 0 in slot 2 memory location. Not the actual slot, not the actual input module, but a memory location that represents that input module a split second before that. The rung is true. It executes an output energize to turn on the bit in memory O:1.0/1. It doesn't turn on the LED. It turns on the bit in memory. Then when the processor does the I/O scan again, it takes the state of the bits in output:1.0, that word, and sends them all out to that output card. Consequently, because we turned on bit 1, it turns on that LED. Now we have two LEDs. we have one hooked up to bit 1 and bit 2. We did not hook one up to bit 0 because the congestion of the graphics to run a conductor over to what would have been bit 0, but we could have done that. So now we have two LEDs, each connected to separate outputs, bit 1 of output word and bit 2 of the output word. The memory locations that the instructions address are represented in green. We downloaded 2 rungs of logic, each controlling one of the 2 LEDs. Now, this really is a sidetrack from what this presentation is all about, but I couldn't pass up the opportunity to emphasize what we're going to do next in this presentation, because this seems to be the single most confusing point for people that are new into PLC programming. Both rungs examine bit 0, the input word. They both address the same bit of the input word, but they are opposite in purpose. The top instruction is a true if on, and the bottom instruction just below it is a true if off instruction. Sometimes you want to do something if it's on, and sometimes you want to do something if it's off. One is true if the bit is on, and the other is true if the bit is off. The bit is off right now, so the second rung is true. It addresses bit 2 of the output word to be on, and consequently the LED is on. So right now, without pushing any buttons or flipping any switches, they're off right now. You have an LED that would be on if we put this PLC in the run mode. We'll just say it's not in the run mode right now. But we wanted to illustrate the difference between a true if on and true if off. And you remember that I emphasized the difference between true, false, and on, off. So that bottom instruction that has the slash through it, you say, well, that's on. Well, it's not. It's true. So the green highlight just means it's true. It doesn't mean the bit's on. Okay, logically, it's true because it's true if that bit is off. So the memory location O:1.0/2 is on right now, so that LED is on. Never forget that in simple ladder logic diagrams, everything to the left is a true or false condition. The last instruction to the right is either on or off. Now this is in simple ladder logic diagram. In something such as RS Logix 500, when you're working with Slick 500s or Micrologics, or almost anybody else's PLC, when you're working with the Logix engine, which is the control Logix, compact Logix, soft Logix, drive Logix, that's a whole different platform. You can write your code so you have condition, action, condition, action, condition, condition, action, action, action. So it's a much freer form of writing your code. But in simple LLD, ladder logic diagrams, everything to the left is a true or false condition. And the last instruction on the right is either on or off. It's on or off based on whether or not the rung is true or false. Now, if the rung is true, that last instruction has an action. Most of them have a true and a false execution. There are some instructions that have a true only execution, so you have to, and by the way, if you haven't gone through the manual and completed the lab projects, the basics, Advanced 1 and Advanced 2, then some of this is Greek to you. Well, if you're Greek, no offense, but high-level language. Okay, this is a good stopping point. We're getting close to 30 minutes, and we don't want to bore you to tears, so we will continue on with 1.1. So thank you for watching Building an Advanced Trainer with Analog version 1.0. So go look for the same title, only version 1.1. Thank you.